Hello there, and in this video we're going to continue our discussion on moment generating functions. So let's just recall what a moment generating function is. So last time we defined the moment generating function of a random variable x, which is a parameter of some function t, to be equal to the expectation of the random variable e to the t x, which from the definition of the expectation is just going to be equal to the sum across all values of x of the random variable value e to the tx times the probability associated to that value of x. And also we proved the property that the nth moment of the random variable x, or the expectation of the variable xn, is just going to be equal to the nth derivative with respect to t of the moment generating function m sub x of t evaluated at t is equal to 0. So let's work through an example of how to generate a moment generating function and use it to generate the moments and also the variance and standard deviation of the random variable x. So let's assume that we have a discrete random variable x and its probability mass function p of x is defined to be equal to, let's define it to be equal to 0.2 for x is equal to 1, 0.3 for x is equal to 2, 0.3 for x is equal to 3, 0.2 for x is equal to 4, and 0 otherwise. So it's very easy to see that this function p of x is actually a probability mass function because the sum of all the probabilities is equal to 1, and also all the numbers are between 0 and 1 and are positive. Also note that this function definitely has some symmetry associated to it. This is related to a moment that we'll discuss later down the line, but at least observe that there is some symmetry according to this distribution. So, therefore, we need to calculate the moment generating function so we can calculate the moments of this random variable x. So, from the definition, mx of t is equal to the sum across all x values of e to the tx times the probability associated to the value of x. So if that is true, then what is this going to be equal to? So the first x value is going to be 1. So this is going to be e of t times 1, and the probability associated to 1 is going to be 0.2. Plus, so the next tx value is going to be 2, so it's going to be t times 2, times the probability associated to 2, which is going to be 0.3. We're going to continue this for the other values, so t3 is going to be 0.3, and then this is going to be e t to the fourth, and that's going to be 0.2. So I can rewrite this in a nicer way, so mx of t is just going to be equal to 0.2 e to the t plus 0.3 e to the 2t plus 0.3 e to the 3t plus 0.2 e to the 4t. So this is the moment generating function of my random variable x. So this is a very, very important tool. So let's just calculate a couple properties. Firstly, the 0th moment of the random variable x. So we're just going to plug 0 into our moment generating function. So e to the t is going to go to 1 because e to the 0 is equal to 1. So this is going to be equal to 0.2 plus 0.3 plus 0.3 plus 0.2, which in fact does equal to 1, as the 0th moment of a probability function should. So let's first off take the derivative of our moment generating function. So the first derivative of our moment generating function with respect to t is going to be equal to, so the derivative of that term is just going to be 0.2 e to the t. Derivative of this by the chain rule is going to be equal to 2 times 0.3 e to the 2t. And then the next term by the chain rule is going to be equal to 3 times 0.3 e to the 3t. And finally, this last term, we're going to have 4 times 0.2 e to the 4t. So that is the derivative of the moment generating function. So remember what this gives us. So the first moment is equal to the first derivative of the moment generating function evaluated at 0. So all the exponentials are going to go to 1, so we're just going to be left with 0.2 there, plus 2 times 0.3, which is 0.6, plus 3 times 0.3, which is 0.9, plus 4 times 0.2, which is 0.8. So therefore, the expectation of x, or the mean of the random variable x, is just going to be equal to 2.5. So that's the mean of the random variable x. All right, so now let's move on to the second derivative of the moment generating function. So the second derivative is just going to be the derivative of that expression. So the first term is just a basic exponential, so it's just going to be 0.2 times e to the t plus, so I'm going to take the derivative of this next term, so I'm going to bring down my 2. So that's going to be 2 squared times 0.3 e to the 2t. Plus I'm going to bring my 3 down for this next term, so it's going to be 3 squared times 0.3 e to the 3t. And then I'm going to bring down my 4 down again, so I'm going to have 4 squared 0.2 e to the 4t. And I'm not simplifying these exponents directly because you may see an easy way to generalize this to, say, the kth derivative of the moment generating function. So it would be 2 to the k, 3 to the k, 4 to the k, and so on. You know, being able to identify patterns as quickly as possible is definitely advantageous. So I'm going to evaluate the second derivative at 0. So that's going to give me the second moment of my random variable x. So this is equal to my moment generating function's second derivative evaluated at 0. So that's going to be equal to, so we have 0.2 plus 2 squared is going to be 4 times 0.3 plus 3 squared is going to be 9 times 0.3 plus 4 squared is going to be 16 times 0.2. And then we can calculate these products. So we have 0.2 plus 1.2 plus 2.7 plus 3.2. And then once you calculate all those sums up, you have that the second moment of the random variable x is equal to 7.3. Right, so we have that the second moment is equal to 7.3, and our first moment, e to the x, or e of x, is equal to 2.5. From these two components, we can calculate the variance and standard deviation. And if you want to make it an exercise for yourself to calculate the third, fourth, and fifth moments, you can definitely go ahead and do so. And there are results associated to them, of course, but we won't discuss them at this time. So let's calculate the variance of our random variable x. So we know that the variance of x is equal to the second moment of x minus the square of our first moment of x. So if that is the case, then that means the variance of x is going to be equal to the second moment, 7.3, minus the mean, 2.5, the quantity squared. So once we have that, we're going to have that that's going to be equal to 7.3 minus 6.25, which is of course equal to 1.05. So if that is my variance of x, then I can calculate my standard deviation of x to be equal to the square root of 1.05, which is equal to approximately 1.02. So that's the standard deviation of x. And that is an example of how to calculate the moment generating function for a at least discrete and finite probability mass function, and also how to use it to sort of generate the moments and the variance and the standard deviation of that random variable.